Okay, so today we're beginning chapter 2 in Algebra, Properties of Real Numbers. So 2.1, the very first section, is called Using Integers and Rational Numbers. So in this section, you're going to do something like you did if you had me in pre-algebra. We're going to make kind of a nesting of a bunch of boxes. So you need to go down about seven lines and create a giant box. So go down about 7 lines, and we're going to start right here in this smallest of boxes. Because we find that with numbers, we have sets of numbers that could be put in other sets of numbers. Kind of like those Russian nesting dolls, where you can pull them apart, and there's a smaller one. Pull them apart, and there's a smaller one, all the way down to a little teeny one inside. Okay, so when we're talking about sets of numbers, and you can see my number line in the classroom, the blue numbers there begin with number what? 1, right? And then they go increasing to the right. So 1, 2, 3. And that set of numbers that we start with the number 1 has a name. And who knows the name? It's a set of... Actually, you know, in Sesame Street, they have a character that represents this. He goes 1, 2, and his name is Count, right? The Count? Count. What do they call him? Count? They just call him the Count, and guess what he's always doing? Counting, right? So these are the set of counting numbers. There's another name for this set of numbers. Just the blue numbers you see on my number line, Ronnie. See them? It begins with the number 1, and then it continues up 2, 3, 4, 5. Then the other name begins with N, and we call it the natural numbers. These are the natural, like in nature. If you were going to count the number of rabbits, you would, there's 1, there's 2, there's 3. You know, you start with 1, the first one you see. So probably the first people who ever counted began with the number 1, not the number 0, which you might think is such a simple number that it would be part of it, but it's not. When we add the number 0, which you can see on the number line is what color? Black. When we add that to the counting numbers, we now have a new set of numbers. And that set of numbers is the set of... It has a 0 in the word. It has an O right in the middle of the word. Say it. Whole numbers. So when you add 0 to all those counting numbers, you have whole numbers. So you can see that the counting numbers are nested into the set of whole numbers. See that? So whole numbers include all the counting numbers, but whole numbers also include 0. So it's a little bigger set than the set of counting numbers. Now, the next set, if we include all of those whole numbers and all of their opposites. So on that number line on the wall, we have those red numbers that are negatives. -1, -2, -3, infinitely to the negative, right? We now have a set that we don't use this word as often in the real world. It begins with I. It's a set of integers. So integers are whole feeling. If I have 1, I could have 1 whole class, right? If I have -1, could I have -1 whole class? But doesn't it feel like you could imagine a -1 whole class? You could imagine it to be whole, the whole class. It feels whole, but it's negative, so of course it isn't whole. It isn't a whole number. So those kind of counting negatives are included with the whole numbers, and we have now the set of integers. Okay, so now the next one up is if we look on that number line on the wall, we know that between the numbers there are other numbers, right? So somebody give us a number that comes between just the 0 and 1. Brian? He said 0.5, so he just gave it as a decimal. And let's take 0.5 and transform it to a fraction. It is 1/2, right? Or somebody said 5/10. There's a lot of ways you could say that. When you take those little pieces that come in between all these whole things, whole feeling things, these integers, then what do we call the set? You remember? Fractional is rational, right? Remember that little thing we sang? Fractional is rational, divide. Okay, so rational numbers, guess what? They include all those little fractional pieces between numbers, as long as those fractional pieces are very predictable. They've got to be predictable. Either they end, like Brian said, 0.5, 1/2. It terminates at the 5. Or it could be a number that repeats forever. Give me a fraction that is a repeating decimal, Shay. 1/3. 1/3 is what number repeating? 3. So 0.3 repeating forever. You could write that as, 0.3 with a line over the top. So it repeats forever. So the millionth digit out there to the right is 3 for that one. We usually round those numbers when we're using them. We can't go forever, so we round them. And that entire set of numbers, there's one other type of a number that's not rational. So if it's not rational, it's irrational. So who can describe an irrational number then? Okay, Stuart. He says 5 divided by 3, but 5 divided by 3 is 1 and 1 point what? 1.6 repeating forever. So that is rational because it has a pattern. It's just 0.6 repeating forever. Gavin. Like pi. And what is pi? Okay. And so what about pi makes it irrational? Because I see it there. It looks like something we could use. Gavin? It has no pattern and it never ends. Okay? It never ends. So pi is the most famous example, but who remembers the other common examples of irrational numbers from last year? No one remembers? Give me, Emily. When you take the square root of... Okay, so what number might we stick in the radical to show irrational, Brian? So 5. So is 5 a perfect square number? No. So any number that is not a perfect square is stuck inside a radical like that is irrational. So it's like pi. It has no pattern. It goes on forever. When we use it, we actually use a rounded version of it. We don't use the exact. Okay? So that whole group, square root of 5, square root of 6, square root of 7, square root of 8. We can go on, square root of 9. Is that irrational? No, that's rational. We can find that root. It's 3. But square root of 10, square root of 11, square root of 12, square root of 13, square root of 14, square root of 15. And then we skip over square root of 16 because that one's rational. We know it's 4. Okay? So those are your irrational numbers. When we take all of these numbers, rational and irrational, we have the set of numbers that we actually can work with. We can work with irrational numbers like pi. We can work with that. These are numbers that we call, you see the word up here, everybody say it? Real. They're real numbers, the entire set of real numbers. So, Teddy asked the question, what was your question, Teddy?
All these are real numbers,
So what's a fake number? So in math there actually are numbers that are not real numbers. Does anybody know what I'm talking about? Non-real numbers? Brian? Well, those are variables that represent a number, but there's something that is not real. If you are not real, you are something that can be kind of dreamt up. It begins with I. If you are not real, you are imaginary. That's it. We have imaginary numbers. And the definition of imaginary numbers, so we can show that with a little cursive, lowercase I. And the definition would be square root of, who was it who said it? Somebody said it. -1. Okay, so what is the square root of 1? 1, right? Just 1. So the square root of -1 is what? Now imagine, what times itself equals -1? -1 times -1 is what? 1. So can you imagine a number that when multiplied to itself equals -1? That's the imaginary number. And actually the best, you can use these numbers, we just can't simplify it. I can't tell you what the square root of -1 is, but if I take the square root of -1 and multiply it by the square root of -9, what do I have? Very good, I have 3 because square root of -1 times the square root of -9 can be put into one radical, right? And together we have the square root of 9, which is 3. Okay, so you may not be able to simplify square root of -1, but you could use it. Absolute value. Give me the absolute value of -10, Vaughn. You know, Cammie? Absolute value of -10. Look on the number line. Absolute value of -10, Jay? 10. And what's the absolute value of 10? 10 as well. So what is absolute value? Jake?
Distance from 0.
Good job, the distance from 0. It's always a positive thing. We're going to walk away from 0 to the number. How many places did you walk? It's a positive distance. Okay, so here is the symbol for absolute value. It's like railroad tracks. And what you see inside, we want to find its absolute value. Sometimes it's a single number and sometimes it's more. Absolute values are grouping symbols. So you may have to simplify what's inside. The absolute value of 2, Ronnie.
2.
Ronnie, the absolute value of -2.
-2.
Thumbs up if you agree. She says -2. Really, the absolute value of -2 is 2. It's also 2 from 0. So look at up here. How far away is this number from 0? -2 is 1, 2. See? And how far is 2? 1, 2. They're both the same distance from 0. Now, when you see the third example, there's a negative outside of the absolute value. So what is the negative absolute value of 2, Cassidy?
Would be -2.
Excellent. Okay. So you just take the absolute value of 2, which is 2, and then take its opposite. The opposite is on the outside. Okay? So, Cameron, what is this one? The negative absolute value of -2 then. Tell me, what's the absolute value of -2? Just that part. The absolute value of -2, just that part? 2. And now you're going to take its negative, so the answer is -2. Good. Okay, so simplify your grouping symbol and then apply whatever is on the outside if you need to. Okay? Let's try evaluating an absolute value. If A equals -3/7, then answer these questions. And come back and check your work. This is what you should have. The second one is probably the toughest one, right? Let me do a different color, this one here. Because sometimes people are tempted to treat absolute value like parentheses, and it's not the same. If I was to write negative of -3/7 with parentheses, what operation am I using now? Multiplication. What number is outside of here, outside the parentheses?
-1.
1. So this is just -1 times -3/7. See? You multiply two negatives and you get a positive. So that equals 3/7. But this one says take and find that part first and then take the opposite. Okay? So you got to be really careful. There is a difference between the two. Okay, then let's talk about opposites. Give me a number, any number, Vaughn. 5. So you gave us that number, 5. Give me the opposite. -5. So what do 5 and -5 have in common, Emily? They both, there you go. What do we call that? Distance from 0 is? Absolute value. They have the same absolute value. So opposites have different signs, but the same absolute value, right? Same absolute value, but one is positive and one is negative. Okay, so we're going to try this. And if you are watching this by video, pause, come back to check your work. Okay, the opposite, you're right, is 3/8 because it has opposite signs, right? But now absolute value, what is the absolute value of the negative 3/8? What is the positive distance from 0? 3/8, it's also positive. Okay, so we have two answers for each. In the first case, the positive number has a negative opposite and a positive, they all have positive absolute values, right? Look at the second answer for each of these, they're all the absolute values, they're all positive. Now the opposite depends on whether you started with a positive or a negative, okay? The final topic is conditional statements today. And a conditional statement is some statement you could make based on some condition. There's two parts to it. And the two parts are often containing the words if and what? What goes with if? If and no. Well, actually, that's interesting. Sometimes that is combined with if, but it's actually a TH word. If, then. If, then. Okay? So if something is true, then we can say something else. An example might be if I don't know. Let me think. So to prove a statement is false, you simply need one example that proves it to be false, and then the entire statement would be false. So here is my statement for you. If you jump in a pool, you will get wet. So don't say anything out loud. Think about that. Is that a true statement, or can you come up with a counterexample? Notice that this statement has an if, but it doesn't have a then, does it? Can you identify the hypothesis of this statement? Jake?
Hypothesis, yeah. Would.
Well, the hypothesis is the if part. So what is the if part of this sentence? If you jump in a pool. Okay? That's the hypothesis, is that somebody's jumping in a pool. And then the conclusion is the then part, and it's not always containing the word then. But you can see the conclusion in this case is you're going to get wet. You'll get wet. So is this a true statement, or does anyone have a counter example to this? Were you going to give us a counter example? Okay.
The pool could be empty.
Okay, the pool could be empty. And so it's empty, so are you really getting wet? No, so it's not true that every time you jump in a pool you get wet. Right? It could be drained. Also, what else? Another counter example. So you could wear a dry suit, you could be in a hamster ball, the water could be frozen. There's a lot of counter examples. Okay? I guess you call it a people, not a hamster ball. Is this true or false? If a number is an integer, then the number is either positive or negative. Shh, don't say. Think about it. Jot it down. Any counter examples out there? Anybody? Or who thinks it's true? Anybody think it's true? It could be that it is true today. Who has a counter? Ada.
What if the number's 0?
Aha. What if the number is 0? Is 0 an integer? Wait, is 0 an integer?
No.
Is 0 a counting number? Is 0 a whole number?
Yes.
Are all whole numbers integers?
Yes.
So it is an integer. 0 is an integer, and is it positive or negative? No, so it is the counterexample. 0 is neutral, so that is a false statement because of that one and only one counterexample. Okay, last one. If a number is negative, then the absolute value of the number is negative. Anybody think of a counterexample? If a number is negative, then the absolute value of the number is negative. Can anybody give me a counterexample to that? Shake.
Well,
The absolute value of negative 3 is 3. Then the absolute value of the number is negative, so you're saying just use an example of negative 3, and that proves this to be false. Who agrees with Shay? This is false. You are correct. Ooh, it's the very example I had up there. Very good. Great minds think alike. Okay. And there you go. Have a good time.